Yes.
Have you already gone over that? Did I miss that? Or?
No, you have not. No, you have not. So that's first announcement. All right. Second announcement here, let me pull the screen down here, is that, I wanted to leave it up before I finish the announcement, is I'm going to cover this in just a second, but remember the review here for the half test is today at 4 o'clock here in PS 116. And so hopefully we got some split time in here for those of you who have math at 5:30. You can still make it, and those of you who might have some obligations that are still going on till 5 o'clock, get here after 5 o'clock here. And Don wanted to see how far we got today. Here he put together the review or the little sheet for the review. I don't think he's had a chance to pass this out to you yet. You guys have this? I don't think you do. Okay. He kind of implied when he said it like you did, and if anybody needed any extras, they were up there. But I'll put them there, and maybe that's just what he had. I should talk to him. Maybe he'll make more before this afternoon. But that should get you started for the final step, which is your test on Thursday. Okay. And so what we have today is simply these sections that hopefully we will get to. We'll see how time goes. But this is what I'm thinking, at least at this moment. We'll see how far we get before today's over. I wouldn't want to put anything on the test that I haven't officially covered here. But as I got to looking at it over the weekend and this morning here, I got to thinking that this might do the best for your overall education and what you get exposed to. Because remember, this whole semester is like that, but in particular at this end here, is to get you just more acquainted and familiar with these, what we call the modern physics, the relativity and the quantum mechanic effects, and so that you'll be pre-exposed to those as you go further on in your education. And that's why I really want to make sure I kind of jump over into these next chapters here, so I can give you maybe the main piece or the main theme here. So we've already done this. We've already done this in relativity, and we've done a lot of this. We did these first two right here, and I'll review those in just a second. But we'll go to Compton effect, and then the rest of this chapter, which then leads into this kind of, hopefully naturally, we'll see the main point I want to get at. So I say all that because this will be what I would call my review for you as we say, look at what's going to be on the test there. And then one more announcement, if anybody has time this summer. I don't know if you are around, but I am in the need and the look for somebody who would do some tutoring over the summer for our 101 class. And it would be 2 hours a day. It would be 9 to 11 for Monday through Thursday. So come talk to me after class or send me an email if you're not too busy doing other internships or classes yourself. But it really needs to be in that window of 9 to 11. That's what I really need. And it's Monday through Thursday. And for 5 weeks. We don't have tutoring the first week and then the next 5 weeks. I think that comes out to be a total of 40 hours. Yeah.
So I typically don't like to be the what's going to be on the test guy.
Oh, okay. Well, but what's going to be on the test?
That's hugely daunting, especially considering the short time frame that we've had to spend with this material. It's fascinating. And
is this taunting?
No,
or this?
It's more that. It's more the 8 sections from 39 and the 7 sections, the 9 sections from 39 and the 7 sections from 40. I mean, I'm going over the 39 material, and I feel like it's going to be a challenge to cram like the Doppler effect in for one thing. Or I mean, it's like I need to focus my energy for these sections because I have such, especially since finals are next week as well.
Okay.
I have such little amount of time. I really need to be like.
Well, I'll tell you what.
Precision.
This is huge. I agree.
Okay.
And we did all of that.
Okay.
And I think we did that justifiably and a while ago. This is rushed, agreed. So let me make sure I just get to the conclusions of this, and maybe I can summarize it at the end. And I don't think what I do here, this one section, and I even put a question mark. This is kind of a repeat of this. So if that's going to make it any easier, I'll cross that out here. But you'll see this isn't too bad, and hopefully you'll see this isn't too bad.
I mean, should we be focusing on like the Lorentz transformations, for example? Should we be like what?
Well, that would be one thing in here, yes.
In terms of setting it, because
Yes,
I actually
Lorenz.
disagree a little bit. I don't feel like we've given proper time to, not like we have to to a lot of the other material in the course. I mean, we've spent considerable time with just about every other unit, and this unit we haven't had a whole lot of time. We haven't really done labs for a lot of this material. You know, we.
You just have to end the class. Like, I want to do it the last class.
Okay, well,
It's really go fast enough.
No, like this is the last class. we have it in before the final exam, which is a huge chunk of our grade. So,
yeah. Well, there's not going to, there's more here than there is here, and I agree that there is a lot here. But I have to say, we did that. Maybe a little rushed, but we did that, and so that's what we did. We did the energy.
I should focus my efforts on chapter 39.
Definitely on 39, and then just a few little pieces in here.
All right.
Yeah.
Thank you.
Yeah.
Appreciate it.
Yeah. And maybe I should answer that better. Go to the review. Don knows what I've done in the past, what I will do again, and he will really shorten the review up. There's just there's a lot here because this is a repeat of all the mechanics. All right. Well. Let me get started then and do as much as I possibly can here. But here's what I want you to see. And I kind of wanted to have all these three done in the last lecture, and we fell short in the Compton effect here. But let me just review here, because this is actually the key. If you understand these, then I'm hoping I'll get the main theme across to you, and that is, what is quantum mechanics? Why is the energy quantized? And if I get nothing else across, that's really what I want you to see and get prepared for that. So here's what we did. We started with Planck here in the black body radiation. And in the black body radiation, we put this little diagram, E, and Planck said that the explanation for the spectrum can be given if you assume, without explanation. He's not trying to justify it in any way. I will hopefully be able to do that for you in here, section 7, and then use an application here. All right? And so that's where I'm headed with this. But Planck just said that the energies are quantized. He did not explain why. He just said if you're willing to accept that the molecule comes in only quantized packages of energy, in integrals of HF. And so each one is one bigger than the one before. If you're willing to accept that without explanation, then I can give you a derivation that would derive the same spectrum that is what we see. All right? And again, we call this the birth of quantum mechanics, because he didn't even believe it himself. He just says, look, this is what happened. Then we left off, and this is the lab we will do actually this week. Some of you will do it tomorrow, and the others of you will do it on Thursday. But this photoelectric effect was Einstein's same approach. Einstein said if you take a photon, if you take some light, and you hit a piece of metal, or it doesn't have to be metal, but some material, what will happen is it will kick the electron off. And it'll be a collision, if you will. And Einstein said the way to explain this is to think of this light not as a wave, but as a particle. And that's the important lesson here. Einstein said, look, we'll take what Planck did, where Planck said the molecules have to be quantized in a certain level and then they give off the light. So then Einstein said, well, if that is true, then the photon that comes in must have an energy of HF. Because what would happen is the molecule that gave off the light would go from here to here. Or maybe from here to here. Or maybe from here to here. But whatever energy state that molecule is in, as it goes to a lower energy state, it can't go halfway. It's either got to give all of its energy or none of its energy. And again, without explanation. Again, and hopefully the explanation will come in here a little bit better as history goes forward here. But this was what we called the photoelectric effect. And Einstein explained it by saying, well, if you think of this light as a particle, photon, it has this much energy. This is what we get from Planck's explanation. Where would it go? Well, it would be the kinetic energy and what is called the work function. How much energy does it take to break free? And so when this hits here, it has to break free. And if you think of the light as a wave, you don't get this equation. And you don't get what was noticed in the experiment. And just to repeat real quick as we get started, this is what Einstein or the experimentalists who were doing it noticed. They thought if you just made the light brighter, or if you made the light brighter, that would make these electrons come off at a faster speed. And that's what you would think if they were waves. You would think if you made the light brighter, what you are doing is you are making the electric field stronger, and so when it hits that electron, it must kick it off. Well, that's not what it was observed. And Einstein said, we can explain this if we think of light as being photons, as if we think of them as being particles. Now, probably none of this is too foreign to you, because we started chapter 35 that way. We started chapter 35 by saying some experiments will show light behaving as a particle, and some experiments will show light behaving as a wave. And most of what we've done since we introduced that in 35 have been waves. We did the double slit experiment. We did the single slit diffraction. We did the thin film interference. All of those use the wave nature of light. It wasn't until we got here and here that we've actually even talked about an experiment that would be a particle one. But this is it. This was a very important piece, and probably the most important piece to get to what I really want you to see here with the quantum mechanics. But again, without explanation, Einstein runs with this and says, I can explain why when you turn up the brightness of the light, these electrons don't come out any faster, you just get more of them. Because his argument was, when you turn up the brightness of the light, you're not treating them as waves, you're not making the intensity or the electric field any stronger. What you have are more photons. And each photon kicks off an electron. And so Einstein was the first to explain, that's why he got the Nobel Prize for it, but he was able to explain that if we think of light as particles, then there will be an explanation for what's going on. Yeah.
So the electric field from light is always the same regardless of how bright it is?
Well, when you think of it as a particle, yes. Because when you think of it as a particle, you are thinking of it as its brightness is how much energy it has. Every photon has the same amount of energy. And so when you say you turn up the brightness, what you mean by that is you just have more photons.
So you have a greater electric field.
Well, if you look at it as a wave, you'll say a greater electric field, sure.
How does the electric field not have an effect on the electron?
Because this experiment, the electrons are choosing to show their property as particles.
But if you put an electron in an electric field, it moves it.
So then it's showing the properties of waves. So the light,
So one or the other.
sure. And maybe I'll go back to chapter 35. Are you a student or are you an employee? And as the experiment is run right now, I'm looking at you in class asking questions. I'm saying, you're a student. But if I went to your job site, and you were, I don't want to guess, bagging groceries at Vaughn's, and I was standing in line seeing you bagging grocery at Vaughn's, I'm going to look at you and go, you are not a student, you are an employee. So depending on the experiment, the different properties can show up. That's why, again, probably the hardest thing to explain here is light a particle or is it a wave? And the answer is, it's both, right? And that's why we use that word wavicle back in chapter 35. And that's why I said I felt uncomfortable with him starting optics with this such deep piece of science that doesn't really even show up till 1905. But now we're there. We finally got into the 1900s here. And we're starting to see experiments. And I want to get to this third one. Because all three of these experiments show that light is behaving as a particle. So we cannot just blow off light and say it's a wave. We also can't blow it off and say it's a particle. it can behave differently at different times, depending on the experiment. Okay? So, let's go to this one. And I'll do it kind of quickly. Here's the picture, and here is what you probably saw in the book if you got a chance to read here in the book here. But this was Compton's experiment. Compton did this. He just took an electron and he freed him up. And so without going into the details of the experiment, he just had a box with these electrons floating around inside. And then he were to shine light on them. So it's kind of like the photoelectric effect, except the photoelectric effect, the electrons are not free. They're in a piece of aluminum. Here, the electrons are free, and we're going to shoot light at it and watch what happens then. Yeah.
What is a feeder? What does that represent? Is that a constant?
Oh, well, Einstein called it the work function. And is it a constant? Yes, it is a number. It is a number that has to do with how much energy does it take to break the bond that is holding that electron on there. So there'd be one number for aluminum, one number for gold, one number for silver, right? And so this is, and I should emphasize, this is a conservation of energy statement. This is the initial energy going in. This is the energy that the photon has. This then is what I would call the final energy, meaning how much energy did it take to break the bonds, and then how much is left over for motion. In fact, maybe I'll save a little time here and say, it'll be a while, but grab a pair of cool glasses here, and hopefully the grand finale at the end will use our cool glasses. Yeah.
After the photon strikes the electron, is the photon gone?
Yes, and then the photon's gone. And so it has given up all of its energy, and it's gone, just like it was created. So, before I turned on the lights, there weren't any photons. I turn them on, and now we are creating photons. They come down, they hit, and they get absorbed. They're gone. Usually we think of that hitting as warming, so we go stand in the sun. That energy turns into warmth energy. But the photons are gone, yeah. There's no such thing as conservation of number of photons like there were for the number of electrons. Yeah. So looking at this picture, yeah.
Does the energy of HF get converted completely into just vibrational energy for whatever molecule or electron that is?
If it goes to heat, yes. In this case, where the energy is not going to heat, I would say no, it doesn't go into vibration, but all the energy gets converted into something else, right? And in this case, it's a free electron, which would be awesome if we were building solar cells here, right? We can then collect those free electrons, right, and make electricity out of it. And so this is a kind of the picture that happens in our photovoltaic cells. We don't actually hit it hard enough to make the electrons free, but we hit it hard enough that it breaks free from the atom and it conducts and becomes part of the electrical circuit there. Well, let's look at this third one here and this Compton one here. If you look at what Compton did, hopefully this one should bother you in the same way it bothered Compton. I mean, if you look closely at it, here's what he did. He sends in a photon. So here it is. It has some frequency or some wavelength. It hits this electron. And then notice, the electron goes scooting off to the side. The photon goes flying down below. There's a new frequency and a new wavelength to this photon. So here comes, exactly, that's why it should bother you. Here comes this photon, hits it, pew. The electron goes shooting out, the photon goes shooting down. Doesn't that kind of sound like a particle? Right? So again, this too is an experiment that, unless you accept viewing light as a particle, it's going to bother you. More than that is look closely at the momentum. All of a sudden, this electron that wasn't moving now is moving. This electron got momentum. I mean, it's moving, so it got energy. That's probably not too much of a surprise, because you're thinking, well, where did it get its kinetic energy from? Well, the photon was coming in. How much energy would the photon have? Well, if we keep the idea from Planck, which then Einstein kept, and Compton keeps, if you keep that idea, you're going to say that this photon coming in can behave as a particle. And not only that, but it has energy. So the fact that it hits an electron and makes it go shooting up at some angle phi. And the fact that the electron then has some kinetic energy probably doesn't surprise you in the sense that this photon has a different frequency now. Because if this frequency is less than that frequency, doesn't that mean the photon now has less energy? And that kind of makes sense. Where did its energy go? Into the electron. But did you catch also the momentum? That's the more interesting addition here.
So the photon doesn't change its speed. It's still the speed of light technically.
Yes. But what you're noticing is, didn't this electron gain some vertical momentum? Didn't this particle, this photon, go down? What does that mean? It means that not only this photon can be thought of as a particle and have energy, but it must also have momentum. But how can you have momentum and no mass?
Simple. It's relativistic energy.
Can you have both? Well, you certainly can't if you are still thinking this. Right? Of course, that's what we just learned from Einstein, that we shouldn't be thinking that. We should be thinking this. Can something with zero mass have momentum? Well, I suppose only if that's infinity, right? But for a photon, what speed does it travel? So what's gamma? Infinity, right? So can I go infinity times 0 and get a non-zero number? Yes. Can this have momentum? All right, so let's go through a quick step and a quick calculation that Compton did. But what I want to emphasize then is notice all three experiments are telling us really the same thing.
So 0 times infinity is infinity?
0 times infinity, depending on which one goes quicker to infinity or to 0, could be 0, could be infinity, could be 7, could be 8. F of x equals x times 1 over x times a. Let x go to 0. What happens? What happens to this one? Goes to 0. What happens to this one? Infinity. And the limit of all of this is a. And so if a is 7, I would say I have one function going to 0, I have one function going to infinity, and the limit of the two together is 7. I've got one function going to 0, one function going to infinity, and the limit is 5. I got one function going to 0, one function going to infinity, and the limit is 0. I got one function going to 0, one function going to infinity, and the limit is infinity. All right, so there's all kinds of things that infinity and 0 could give me, right? So we got a little math to do. Fortunately, it's not too bad. But I do want to emphasize then what this is saying here is one step more than Planck. So Planck says these are quantized. Einstein says we can treat light as particles, photons. Planck says not only can we treat them as particles that have energy, but they're particles that have momentum. So what should the formula be? Yeah.
Given that, can't you like take the measurement momentum and find actual speed of the photon? Like, if it was actually the speed of light, then it would be 0.
What would be 0?
Or I mean, the gamma would be 0. So gamma would be infinity.
No, gamma would be infinity at the speed of light.
Well,
Right? Gamma is 1 over the square root of 1 minus v squared over c squared. So I'd get 1 minus 1. Yeah, and as v gets closer to the speed of light, this goes to infinity.
But I'm saying if it was exactly the speed of light, then it would be 0 on the bottom. Not
Right.
if getting closer, it would just be 0.
Okay.
That would be
And that'd be?
does not exist.
All right, I think I'm making this too complicated. Let's get away from this. This is going to drive you batty. Let's see if we can find the limit by another means. Because this one goes to infinity, right? And this one goes to 0 as the mass approaches 0. And so can this number be defined? And I'm trying to say, yes, it can be. Let's see if we can take the limit by a different way. It'll be real easy. Yeah.
I'm not sure. Maybe this is what you're going to do, but I was just going to say replace m with e over c squared, and then you don't have a 0 in your equation.
Nah, I'm going to do this. Does this look familiar? From chapter 39? Right? This is where we ended in chapter 39. What we said is the kinetic energy plus the mass energy. And so this was a good discussion about Einstein's discovery that mass is really a form of energy. All right? But this is our total energy. Watch this for a moment. What if I were to take energy, which is gamma mc squared, and square it? Now, that looks a little funny, I must admit. But I'm going to add that, subtract that, and add that. I am going to cheat in terms of algebra and say that if I did a bunch of work here, I would get a gamma squared, an m squared, a v squared, a c squared, and then an mc squared squared. So again, it's not the math that I want you to see. We won't have enough time here to do the math. But the result is, does this look familiar? Isn't this the momentum? And so this is what Compton does. Compton says, let's relook at this whole idea. This object should have momentum. What would be the equation for the momentum of a photon? As you can see, it's a little bit cumbersome to try to get it from here, because you're saying, hey, I have an object that has 0 mass, but it has a speed of the speed of light. How do I get its momentum? And I claim this is not a good approach. I claim this is. And so Compton works through this and he says, look at this equation now. What if I set the mass equal to 0 now? What if you have mass equals to 0? What do you get here? E squared equals PC squared. Or E is just equal to PC. Or there it is. This is what I was after. Is there an equation that would tell me the momentum of a photon? And yes, there is. And so again, want to emphasize, experiment number 3 cannot be explained if you think of these photons as waves, but can be explained if you think of them as particles. And so if we do a substitution from what Planck did and Einstein did, you get this. If we do another substitution, which is going to look a little weird, because remember, aren't we thinking of these as particles? But if we replace frequency with its equivalent wavelength, now remember, I'm not thinking of them as waves right now, and so I'm really kind of doing both at the same time. Again, that's why it's better to call these wavicles than they are particles or waves. But if I do this next substitution, I get hc over c lambda. The c's cancel off, and I get to what's going to be showing a very important idea here, is that not only do these photons have energy, but these photons have momentum. And that would be our equation for their momentum. It would be Planck's constant divided by its wavelength. And so this experiment, like I said, is the first time anybody noticed that light had momentum. And that's the point here of Compton's experiment, is to say, look, if we think of these as particles, then we can explain all of these experiments, including, I think, the harder one to explain, which is to say that these photons have not only energy, but they also have momentum. And that's just really the beginning. Yeah.
Is that how solar sails would work?
Yes, exactly. Exactly. And so if you wanted to send a rocket ship or a space shuttle or whatever into space, all I need to do is absorb the light. Now, granted, I bet most of you do not think of light of having much momentum. If I stand here and open the door and let the sunlight come in, that would be like being hit by a bunch of baseballs. Fortunately, this number, Planck's constant, is really, really small. And probably none of us have really ever thought of the idea that that light is hitting us and pushing us. But the light does carry with it some momentum. Granted, it's not much. And that's why you've personally have probably never felt it, and you would need something small for this electron to even have noticed it, but they do carry with them. And so if you put like a giant mirror in space and the sunlight comes up, it would hit it, and it's better to put a mirror, not just absorb it, but reflect it. So your change in momentum is positive to negative. Then you can push off and go that way.
Could you just keep accelerating forever if you did that?
Yeah. Well, remember, you get further and further away from the sun, so the intensity goes down and down and down. But fortunately, the force of gravity goes down by the same factor, right? The force of gravity goes down by 1 over r squared, but the intensity goes down by 1 over r squared. So whatever acceleration you get, say, near the Earth, you actually keep the whole way, because as you get further from the sun, your force of gravity goes down, as well as your intensity goes down. Yeah, yeah. Or perhaps better still, since that's probably not a much, they're thinking about maybe we should do this. Maybe we should take advantage of multiple reflections. And so put a mirror on the ground and a laser with a mirror on our rocket ship. And we fire the laser, ting, 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 right? And do multiple reflections off of that same beam and see how much we can get. But, good luck lifting a 100-ton spaceship with, that. But worth thinking about. And in fact, I think he's taken it out of this edition, but if you look online, they show some really neat, they've got small nanoparticles with a laser beam. And the particle is just hovering there because the laser beam is pushing up on it. So it kind of looks like what you might see if you put a ping pong ball in a stream of water. This is a nanoparticle in a laser beam. And so the laser beam does give enough upward push to support the weight of that nanoparticle. And so they've been successful with that. They haven't lifted anything bigger than small particles, but one step at a time. But my point here is I really wanted you to see this, because the best thing I think I can do for you guys for your future here is to realize that these were some experiments that really led scientists to say you can't think of light always as a wave. You have to at times think of them as particles. And when you do, we have an equation for their energy, and we also have an equation for their momentum. Now, the reason that is so important for quantum mechanics is because the next guy here, de Broglie, really put it all together. De Broglie, after watching the explanation of these 3 experiments, said, all right, you have just explained 3 experiments that were unexplainable because we kept thinking of light as only being waves. And now if we think of them as particles, we can explain them. So I like to put it this way. Here's what de Broglie is thinking. You can think of light, depending on the experiment, as either a particle or a wave. His question then, what about electrons? We have been thinking them as particles. So what do you think he's going to ask? Can electrons do the same thing? I mean, could it be that in history, here's what we've been doing. We've been running simple experiments that have shown only the wave nature of light and the particle nature of the electrons. Could it simply be that nature is more complicated than that, and that for the first time in history, we're seeing light behaving as a particle, not just a wave? So is it possible that nobody's done an experiment yet to notice the wave property of these electrons? Could electrons be thought of as waves? In fact, interesting side story is he wrote his PhD thesis on that, and the university laughed at him. Go away. And the Nobel Prize Committee said, you know, I think he's onto something. And when he was nominated, the university said, you know what, we better give him a PhD for this before he gets a Nobel Prize for this, or we're going to look really silly. And so he got the two about together, and he got the Nobel Prize for this idea, and he simply said this, that look, what we can do is we are familiar with the momentum of an electron. We think of it as mv. If you prefer, I'll put a gamma mv just because you're more educated, but let's not make it that complicated here today. Let's just say, look, let's take these regular simple electrons that are not going fast to the speed of light, just the kind we use in our circuits, just the kind that are in the atom. Let's just say then that this is going on, and so he proposed that these electrons would have a wavelength. Well, you learned that if you send something with a wave through a single or a double slit, shouldn't that show the wave properties of them? And so, the first experiments were tried. And actually, the first experiments were done by accident. As your book talks about, the Davidson experiment is there was a mistake, if you will, in their experiment. And Davidson was shooting these electrons into, I believe they were nickel atoms, and he was firing them into there, and he was like, something doesn't seem to be working right. He did not get the kind of reflection as he would expect from particles. He got a fringe pattern. Bright, dark, bright, dark, bright, dark. Like you would expect from waves. Like you would expect if you had a thin film. And so Davidson realized, wait a minute, de Broglie's right. This whole experiment I've been doing for the last, 10 years and was going crazy because it wasn't working like I thought it was supposed to work, is really an experiment that is showing constructive and destructive interference for these electrons. And so what happened is the electron bounced off of here, another one went through and bounced off of there, and then you got bright, dark, bright, dark, bright, dark. And so that explained the experiment. And that was about the time where people started taking de Broglie very, very seriously and saying, whoa, could it possibly be that nature behaves like that? This is one of my favorite experiments. So they give it a try here. This is the equivalent of the Young's double slit experiment. They took two small slits and were shooting electrons through it. And after 28 electrons, they got this pattern. After 1,000 electrons, they get this pattern. After What are you noticing? That without question, the electrons are behaving as waves. And they have a wave pattern. And that's really what I want to get across to you, because this really explains quantum mechanics in a nutshell. Because, oh, question?
Why didn't de Broglie just do that right away when he was thinking about this? Why didn't he use a double slit experiment right away?
Oh, I think it was done pretty soon afterwards. But you can imagine the skills and the technique. Usually what somebody thinks and somebody does are two different people that are spread out a little bit in time, because their information has to go to somebody who's got the skills and the technology to do it, and then they got to think if they can do it, and they got to try. So the experiments that are done and then the theory that goes with it, you know, these days are a little closer tied hand in hand, but you know, as we go back in time, they could be years or decades apart there. Yeah.
So do we actually include a gamma in the equation?
I'm going to throw the gamma out because we're going to just take these electrons that are going maybe only 5% the speed of light. And so we don't need the gamma. That doesn't get the point across. You know, the point is the same regardless if we're getting close to the speed of light. The math is just harder if we have fast electrons.
Doesn't it start getting rid of the edge issue as you try to observe what's happening at the double slit?
Yeah. But my point here is, again, just want to emphasize that these now are waves. Because here's really what I wanted to get across here. It's going to take you all the way back to the beginning. Way back when we got started. You remember this tube? Right? It produced sound, right? Did it produce every frequency? Do you remember going through this? Is it worth repeating? Didn't we say this side would have to be an antinode and this side would have to be an antinode? So that means from here to here could be a half wavelength. But it also could be a whole wavelength. It could be 1.5 wavelengths, right? So in other words, if I spin this and make sound, there is one frequency that is possible, or another, or another, or another. But is every frequency possible? No, only certain quantized frequencies are possible.
All these are harmonics.
Certain harmonics? Exactly. And here's my point now. If you think of the electron as a wave, there's nothing special about the electron. All waves are quantized. Remember, the wavelength is related to the frequency. And remember, the frequency is related to the energy. So, all of a sudden, you have an explanation of why there is quantum mechanics. I brought this big one out here to kind of show you again. We did this at the beginning of the semester. But if you think of this as being an electron right here, this is the vibrations. And so this is going to be my electron, not as a particle, but as a wave. And from here to here will be the atom. And if this electron is in the atom, then what can happen is the electron could be doing this. That was what we called the first harmonic, right? That is one possible frequency. But it's not the only one.
Is this wave the probability density?
Yeah. It's the wave. If I square the wave, it becomes the probability density. But you asked earlier, what should you know? And that probability density was not in the section that I covered there. So if you're asking for the test, don't worry about the probability density. But conceptually, yes, it is then where is the electron? The probability density here. So if I were, and this is the point really that I want to get across, if I get, really nothing else today, it's this. That electrons can be thought of as waves. All that other stuff was justification of what made science get to the point of thinking of them as waves. But once you think of them as waves, you understand why they have to be quantized. Because you either have this pattern or you have this pattern, right? But nothing in between. Or you have this pattern. But every pattern that I've shown you so far has a different frequency. And the energy is related to that frequency. So there is our explanation of quantum mechanics, that only certain frequencies are justifiable, just like sound. There's nothing different between the quantization of the sound waves and the quantization of these electron waves. Oh, how do I do? 3? Should I try 4? No, a little faster. Oh, there's 4. Okay. And so that one's faster. But notice that when I did not get the frequency just right, the waves I made kind of canceled out the other waves, and you got nothing. You got destructive interference. And that's the point of our quantum mechanics, that unless the frequency is just right, if the frequency is not at a set frequency, then the waves that form interfere with each other and cancel each other off here. And so, let's do this. Let's look into chapter 41 here for a second. Section 2.
Does that wave have to do with its energy state around the...
Exactly. Now let's run through some numbers. I think it'll make more sense to you when I do some numbers here. But what I wanted to get across was, starting with de Broglie's idea. He takes Compton's idea that if light can be a particle in a wave, then maybe the electrons can be a particle in a wave. And if you think of the electron as a wave, then what we were doing with our acoustics, we tend to do with our chemistry. And if we think of that electron as being quantized, and this is the size of the atom, so let's say I have an atom. That's not quite the picture I wanted to get started. This is the one I want to get started. But if I think of this as the atom, let's make what I will call the worst model of an atom, but a good start to our understanding. Let's just do this. Let's just say that this electron is in the atom, and the atom has a length of L. That's what this picture is trying to say. And that's why I wanted to jump from chapter 40 and actually apply it here in chapter 41. And in chapter 41, section 2, the only part I really am going to care about here in terms of the test is something hopefully you've already done before. Didn't we do patterns like this? Didn't we say that you could have a wave that looked like this? That's what I was trying to show you with this long spring. If that is the pattern, then I would say the wavelength here, or let me do it the other way around. The length of the box is half the wavelength. And if it helps, I'll extend it out to there. But that's not the only pattern I showed you. That was the first one I showed you. That's what we called the first harmonic way back at the beginning of the semester. There is other patterns that are possible, and that's why I called up that picture to kind of jog your memory. That's why I was shaking that spring to kind of jog your memory. So I was spinning the tube to show you that there's either the first or the second harmonic. And in this case, L would be 2 half wavelengths. The next case would be L equals 3 half wavelengths.
In a tube. Is this around the atom? Or is this around the atom? I don't know.
Is this its distance from the nucleus?
No, like I said, this is a terrible model of an atom. Let's get better before the day's over. Okay? But this is our first attempt at an atom. It is really not even an atom. It is just an electron in a box, and that's why your author calls it in section 2 an electron in a box. In fact, maybe it would be worth then going away from this picture from just a second, and before I go into the math, maybe show you some of these pictures. Because unless you don't think these electrons behave at waves, in the last decade, science has really made some incredible microscopic measurements. And these are atoms placed on top of a surface. And they've made this kind of oval shape here. And they put an electron in the middle. And you don't see a little baseball rolling around in there. What do you see? You see ripples. These ripples represent the electron that is inside of my box. This is an actual amazing experiment given this idea 100 years ago. Go fast forward 100 years, and now we can actually measure, we can actually take photographs of the electron inside of the box. Now, this is a two-dimensional box and much more complicated than my simple one-dimensional box, but like I said, this is a poor way of saying what is all of this trying to say. And what it is trying to say here is that you have quantized wavelengths. And you see a more complicated pattern in something like this. I'll show you another one. I think this one is, which is in your book, is why I called it up. But the one that I think I probably should show you is this one. I like this one a little bit better because they put it in a more symmetric box, if you will. But here is the electron in a box. So they just put atoms on top of a surface and they dropped an electron in between. And doesn't this look like you would expect to see if you dropped a rock in a puddle? Right? There's a little puddle or pond sitting out there and the water's nice and smooth and you drop something in there. What would you expect? Yeah, you would expect the waves. And in this case, since there's a corral around it, you would expect the waves to go out and reflect back and go out and reflect back and form a standing wave pattern. And it would be there for quite at least long enough for somebody to take a picture of it. And that's what they did. They're trying to show that, yes, these electrons do behave as waves. And if they behave as waves, the point I'm trying to get across is then there is an integer number of waves, and each wavelength is a different energy, and that's why we have quantum mechanics. That's why in your chemistry class, I'm sure you talked about energy levels. Oh, the electron can have this or this. But what you probably didn't talk about is why the electron can have this or this. And I'm trying to say it's the same reason of the quantization of any wave pattern. Yeah.
The ripple effect we see like on the screen, like, is that electromagnetic waves or is that actually like the electron itself, like matter?
Yeah, no, I'm glad you asked that because now if we can think of electron as waves, your question is what's waving?
Yeah, like what's that?
You see, back here when we thought of light as a wave, we said, okay, the wave nature was an electric field. What you're asking is what is waving? Right? So let me emphasize, no, it's not an electric field. This is not representing the electric field. If they were, I would call these photons in here, not electrons. Okay? And if I knew what was waving, I too would get a Nobel Prize. And that's where I want to go with it. So that's where we are in history right now. That may be your great discovery here, is we don't know. And so just like we as humans and scientists did optics for years and years and years before 1865, before we realized light was an electric wave, that's kind of where we are in history. If this was 1820, we would be doing a Young's double slit experiment. We would say the light is behaving as a wave. A student would ask, what's waving? And I would have to say, I don't know. We don't know yet. And that's where we are with these electrons. So we call these matter waves, because what's oscillating is the matter itself, the electron itself. What exactly is that? We don't know. But we do know that they act like waves because they show up in terms of wave patterns. They explain our quantum mechanics. We have constructive and destructive interference. And we know that it's something, that increases and decreases because we also have what's called antimatter. And so when you take these waves of matter and antimatter, when they align, they eliminate each other. But we don't know what's being eliminated because we really don't know what they are yet.
So it's a sensor that picks this up, and what is it reading?
Yeah.
It's reading it's reading the amplitude of the wave.
But when it's just
And it's plotting where is the amplitude of the wave, the height of that wave. And so it shows really well the wave pattern.
are those almost like energy bubbles?
Well, so it would be how much energy. It's a little tiny micro probe. Yeah.
And then how do they know that those are atoms?
Well, they put them there. They put them there. And again, that's the amazing thing within the last decade.
That's one electron inside the quantum probe?
I said it was one. It may be two or three. I really don't know, but they're acting together collectively because it would be like one photon of light might be so small that my detector can't detect
But
it.
it's a finite number. It's not like
Oh yeah, and they're coherent in the sense that they're all doing the same pattern. So if one of them was too small for my detector to pick up, then I would put 2 in there or 3 in there. And I am not sure how many they need to actually pick it up.
it's not. Is it related to its position? To
Oh, now you bring up a whole question. What's the position of the sound wave? Where is it?
I mean, wouldn't it be moving at a ridiculous speed? The electrons in there, so.
Oh yeah, but they bounce back and forth, so they set up a pattern.
Right. So it could be in all of those locations.
Oh, you still think of it as a particle. You want to know where it is. You're stuck back here in the 1800s.
I'm trying to catch up.
And I'm just teasing you. But what I am trying to say is you see how it messes with your mind, that we have a whole new way we have to look at the things. And the things that can now happen and behave on a microscopic level can be totally different than on the macroscopic level. And it's because of that is the things that will be invented and the designs that will take place in the next decade, 2, 3, are going to be absolutely amazing. And good luck trying to explain it to somebody who really doesn't understand this step, because they want to do this. Well, where's the electron?
It's everywhere.
Right. If I drop a rock in the bathtub and the waves are everywhere, where are the waves? And my answer is they're everywhere on the surface of that bathtub. They're not to the left or to the right of the bathtub, because they're not particles. Now, they are waves trapped in the bathtub, so I would say they're in the bathtub. And I would say the same thing here about this electron. The electron is inside the corral. Where exactly? Doesn't even make sense to ask that question, because it's a wave. It's just, it's everywhere. It's all spread out. Yeah.
So, a couple questions. The
photons are not protons, so are they waves too?
Yes, I wasn't even going to go that far. But after de Broglie asked the question, can electrons behave like waves? I think it was Gamow who had made the next question there and said, well, what about protons? What about neutrons? And yes, yes, and yes to all of those.
And how can a wave have mass?
Think of an ocean wave.
I guess the answer comes back to it's not mass, it's mass energy. It doesn't have mass, it has energy, right?
It has mass energy.
It has mass energy. And mass is really our lack of human understanding of what really energy was to begin with. Yeah.
So it seems like any form of energy can be treated as a wave.
Exactly. So what you're hopefully seeing here is it's not so much that the light can be thought of as both or the electron can be thought of as both. The truth is everything can be thought of as both. And we usually don't see the wave nature of them. When the wave is so small, we don't see interference and we don't see diffraction. That's why when we did our thin film interference, we had to get small. We had to get down to the wavelength of it. Same thing here. For the first time in history, we don't see the behavior of the wave nature until we get down to the microscopic. And like I said, that's probably the best thing I can give you on this last day, is you need to realize that electrons can be treated as particles and waves. And I'm going to do a quick math one eventually here, for the first time, to do a calculation and to treat electron as a wave and see what we come up with and see how it's different than if we think of it as a particle.
So it's kind of like mass radiation in the way like heat just radiates off something, but like mass, the energy, it's like converted from mass to energy and it's radiated or something?
Sure, but let's say the electron radiates, not the mass, so I can stay away from that issue. Yeah. Yeah?
How do they figure out that protons will also weigh? Electrons seem a little more intuitive. What's going on?
Oh, okay, so you're willing to accept the electron as a wave. Fair enough? Yeah, you can see it's a harder experiment because, again, in order to see the wave nature, you have to make things as small as the wavelength, and the proton has a lot more mass. So its wavelength is much smaller. But you can do the same thing. You can take individual protons and you can send them through small slits. And these small slits would probably have to be atoms of, crystals and atoms, and even smaller through a nucleus itself. But you would get the scattering of a proton off of another nucleus. Because remember, another nucleus would be proton, proton, proton. And so the spacing between two protons would be like a double slit. And you can send that through there and get an interference pattern. You would also then get quantum levels. You would get energy levels for the proton in the nucleus like you would get energy levels of the electron in the atom. Many of you have probably done chemistry where you have learned that the electron is possible at different energy levels. And what I'm trying to just show you in this last lecture here today is the explanation for that has to do with treating the electron as a wave, and that the wave has to be an integer number of wavelengths. But the same thing would happen in the nucleus. In the nucleus, the proton can be at one orbital or it can be at another orbital. And so the same kind of things you've learned for the electrons that are on the outside of the atom really happen for the proton inside the nucleus too. And that's, that's where we transition from chemistry to nuclear physics. Yeah.
So you say it's kind of like a rock. So saying the electron like a wave, like it's like throwing a rock into a puddle, right? But obviously the rock and the puddle, the rock and the waves are two different things. But
oh yeah.
But the electron is both the wave, is both the rock and the wave at the same time. So if you throw the electron into the puddle, then you get the
all right, let me change my analogy. Let's take a scoop of water and drop it in the puddle. Okay? So now it's going to make waves, right? And maybe even to make a better analogy, let's just say there's no water on the ground, just a corral. So when I drop the water, now I have waves. The stuff I drop is what is the wave made out of. That's what we have here. And so I thought I'd grab these too. You saw that one. These are black and white. Here is a square, a triangle, a hexagon, a circle. I mean, all these ones, again, just to do it, I guess, because we can. And to show that if you make a corral and you put an electron in it, it will make a wave pattern. Yeah.
Is the entire thing what is considered the particle, or just the wavefront that interacts with your experiment that you consider the particle nature of the electron?
Wait, say that again?
The electron acts like a particle, right, and not like a wave. But we look at this picture that demonstrates what a single electron looks like. Do you say that just the wavefront that hits whatever your experiment is, like a molecule of lead or whatever, is the wavefront like a piece of that wave, the particle version of an electron, or do you say like the middle is, or how do you say what interacts?
Well,
and
there we get into your question that I don't have enough time, what we will call the probability density. So if I were to do this,
yeah, is it like the nodes or the crests?
again, you're kind of asking where's the electron?
It's wherever I put my hand in.
And okay, I would say the electron is everywhere based upon the amplitude of that wave. So I can say 10% of the electron is, say, here. 5% of the electron is here. And I can assign a probability density. The whole thing added up is 100%. I know that the electron is somewhere in the whole thing. Yeah. And so that's where we start to get into the probability density. Okay? But, oh, yeah.
Okay, so if you have one of those corrals and there's an electron moving around, what if you put a center divider down the middle? Now do you split that electron too?
No, you do not. And that's something that we don't really have an explanation for either. I mean, your question was a great one. What's waving? Don't know. The next one is, what if you just put if you put two electrons in there and you put a divider and then you see waves on one side and waves on the other, you're not surprised. You got one electron trapped on one side and one electron trapped on the other. The next question has been tried again and again and again. Let's put one electron in there. And let's see if we can cut the one electron in half, right? Because you could do that with a puddle, right? If I had a puddle and I dropped some water in here and the water went rippling out and I put a divider, I would expect to get half of the waves trapped on this side and half trapped on that side. Fair enough?
What would the divider be made of? Atoms?
But if you put one electron in there, what will happen is as you put the divider in there, you will get all the waves whoosh, quickly onto one side. And half the time you do it, they will go to the left, and half the time you do it, they'll go to the right. So you can't split the one electron. And of course, you're asking, why not? I wish I could give you an answer.
It's one atom.
Yeah, we give the answer that there's something going on more complicated than we understand. It is quantized. The fancy word we like to give it is the collapse of the wave function. It collapses here and shows up over there. But I can't give you a reason why. Nobody knows. But we know that that's the way nature behaves, and we don't have a really good explanation for it. Other than that's our word, the collapse of the wave function. You know, the same thing, well, I'll go on. But many experiments have been tried with one electron, and you never get half an electron.
What about two electrons? We get waves on both sides of it.
Yes, if you put two electrons in there and you put a divider, it always comes out. One electron on one side, one on the other. It's perfect when you have two electrons, or 4 or 6 or 8 or any integer number. But that electron is definitely quantized, and we really don't have a good reason for how that would be different. But then again, the photon does the same thing if you had a single photon. So they're both there. All right, well, as I said, I've been trying to build up to the point. Let me go back to our little picture here. But I really wanted you to see that if you are willing to accept that the electron behaves as a wave, I'm hoping then you won't be nearly surprised that it is quantized. And if we just apply our physics that we learned about waves to the electron, so good news here, nothing new, nothing we haven't seen before, we're just out there applying it to the electron. And so that's what I started to do. I said, look, let's just take an overly simplified model. Let's just say there's a barrier here and a barrier here. I'll call that an atom, but as you can see, that's a poor model of an atom because there's no nucleus. All right? But let's just use it as our first model and hopefully do a little bit better to wrap it up for here today. But this will be my first model of an atom. I just took a barrier and a barrier, and that's what I have. So the first wave we'll call psi 1. And that was your question earlier. I will call it psi because I know something is waving.
So we're measuring.
But please don't ask me again, what is waving? Because I can't answer that.
We're measuring it experimentally, but we can't really.
Right. So again, going back to optics, we are pre-1865. We know our light, we can measure the intensity of light, but we don't know what's waving. Right? So let's apply that idea here. As I said, your author calls this in section 41.2 the particle in the box. Say, look, let's just put an electron in the box. One little electron, what would it look like? And what I was trying to say is it has options to look like this, to look like this, to look like this, but nothing in between. And these are the patterns. So if I go ahead and do a little bit of arithmetic here, maybe I should write out the general pattern, but I think you can see that L would be an integer number of half wavelengths, where N is 1, 2, 3, 4, ... Fair enough? And if I then say, what is the momentum of this electron, which we said the momentum is h over lambda. Let me solve this for lambda and put it into here. So I get h over 2L over n, which of course becomes NH2L. And for the first time today, we actually have an equation for what is the momentum of this electron. And notice it's quantized. That's what I want you to see, right? It would be some integer, 1, 2, 3, 4, 5, 6, 7, times that quantity, h bar over 2L. And hence, the word quantum mechanic. There's only certain wavelengths you can have. There's only certain amount of momentum it can have. We'll do the kinetic energy here in just a second. But everything now becomes quantized. Once you treat it as a wave, just like here, once you treat it as a wave, it is quantized. That's, like I said, the biggest conceptual picture I can get. The rest of this is math that I don't think is any different than we saw before, other than all of a sudden we've got waves and we're talking about the momentum of the wave. Like, what? And now we're going to talk about the kinetic energy of the wave. Okay? And so I'll do the kinetic energy too. The kinetic energy would be 1/2 times mv squared, right? So maybe I should continue this and say momentum is mv, and so this is n times h over 2L, or put another way, v then becomes an n and h over 2ml. And if I put that into here, I get 1/2 m, and then I would get n squared h squared over 2 m squared, squared, so that's a 4, squared, 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 and squared. If I simplify this a little bit, one of the m's upstairs cancels with one of the ones downstairs. And again, not to say this is the best model of an atom. It's not. What this is the best of is this is the best way of showing quantum mechanics, that they're waves. Treat them as waves. If you treat them as waves, you will get their wavelength quantized. You will get their momentum quantized. You will get their velocity quantized. You will get their energy quantized. And there it is, h squared. Yeah.
So we're ignoring gamma for all of these.
Right. Now, again, to keep it simple, especially since we just got done off of a chapter, there should be a gamma in here if it was going close to the speed of light. So I'm still talking slower speeds. And likewise, kinetic energy would not be this equation if we were going close to the speed of light. So I am talking about back to slower speeds, even though I know we just did a chapter close to the speed of light. But getting away, if you remember that little chart I gave you that listed size on the vertical axis and speed on the horizontal axis, and I put a C here and I divided this into 4 boxes, I said this was what Newton did. Newton figured out our science for big objects going slow. And then in chapter 39, we said, what if you had big objects going fast? And so now we're asking, what about small objects that are going slow? That's why there's no gamma factor. That would show up here. And we're not even touching that. So no gamma factor, right?
So the electron's wavelength is a function of its velocity only.
Yeah. Right. So again, de Broglie is the one to blame for all this. There he is, right? He's the one who noticed that there is a direct connection between momentum and wavelength, which is also connected to velocity, which is and the mass, right, yeah.
So what exactly is L in that equation?
So L is the size of this box. Okay? So maybe as a simple calculation, let's use an electron in a box that is about the size of an atom. Okay? And let's put in some numbers here. And so if I go and I look at the kinetic energy, I'm going to leave the n alone here. But I'm going to put in these numbers. 6.63 times 10 to the negative 34. And I'll square that. I'll put in the 8. And let's use an electron in the box. So what's the mass of the electron? Yeah, so there's the mass of the electron. And again, it's a terrible model for an atom. It is a good model for learning. All right? And so again, no nucleus to worry about. Just barriers at the end of the box. That's why we like to say, hey, let's teach this first. And the students are willing to buy into this whole idea that the electron has a wavelength. And if they buy that much, then they should go back to their acoustics and accept this pattern and accept the idea that it's quantized. And we did the same pattern back when we did acoustics, and so I'm just doing that pattern again here. And so as I put this in for the size of the atom, let's see what I get. And so I'll get out my calculator and say 6.63 times 10 to the negative 34, and I'll square that. Divide that by 8. Divide that by 9.11 times 10 to the negative 31. Divide that by 1 times 10 to the negative 10th and square it. And if I do all that, I come up with 6.03 times 10 to the minus 18 joules times n squared. And so if I were to make a plot of the energy of this electron, the first plot would be n equal 1. N equal 1 would be 6.03 times 10 to the minus 18. What's the next energy level it can have?
4.
Right, when n equals 2, it would be 4 times that much. Now again, let me pause here because again, if I can get nothing else across, I know it's been a long semester here, but the whole idea of this explains quantum mechanics. And many of you, most of you even, will at some point go much further into quantum mechanics. And what I want you to take with you from here is that the way you deal with quantum mechanics, the way you handle it, is to think of the electron as a wave. And so that's what we have. And thinking of it as a wave explains why you have a quantized energy. Hang on, let me just multiply this by 4 and see what I get. So if I multiply it by 4, I get 2.41 times 10 to the minus 17. And let me do one more. What would be the next energy level? Well, n is 3. And so it'd be 9 times that original. So let me divide by 4 to go back to my original and then multiply by 9. And so this energy level would be 5.43 times 10 to the minus 17 joules. But again, if I can say nothing else, is notice the energies are quantized. They are quantized because the wavelength is quantized. They are trapped in the box. There's only a certain set of harmonics that can exist. That's what I wanted you to see. Yeah, and so back to our acoustics, what we called harmonics was these energy levels, n equal 1, n equal 2, n equal 3.
Okay, so harmonics coexist with each other, much like when you pluck a string, you can have the first, second, and third harmonic.
Yes, and so when you pluck a string on a guitar, you can only have these frequencies, the first, second, and third, fourth, fifth harmonics. Likewise for an electron. Electron can only have this energy, this energy, this energy. And again, that explains our quantum mechanics.
But can they coexist though? Like, can they coexist with each other? Like, you can have the first and third, or have some level of the second and have some level of third.
Well, it could be in this one, or it could be in this one. And if I had multiple electrons, I could have one in that one and one in that one.
Oh, so only one exists in one harmonic at any time.
Yeah. I'll say that for now. Yeah.
So if we hit the electron from one stage to the other, what's happening in between?
Okay, so there is nothing in between, hence the name, the quantum mechanics. Now, when I say nothing in between, what I really mean, there is no stable state. It would look something like this. Okay, so here is my poor example of an atom, right? Here is an electron in state 3, okay? And so it's in state 3, which means on that picture it's got an energy of 5.43 times 10 to the minus 17. And the electron decides to lose some energy and go to, okay, so oh, sorry. Electron probably does this a little better than me. Ah, there we go. But did you see how the transition from one to another was a little chaotic? And the wave pattern was pretty complicated? And so we say that the wave pattern really doesn't exist between them, but it's really kind of a combination. Watch here. Here's wave pattern number 2. Can I change this to wave pattern number 3? No, I can't. Yay! Oh, that's 4. Okay, so what I'm trying to get by analogy here is between them is a combination of waves made up of states 2 and 3 as it transitions from 2 to 3. But it's only these states that are stable. These are the states where the electron exists, if you will. Does that make any sense? All right, so that's probably the best way to answer it, because here's what I want, the second part I want you to get out of this is what I was trying to do for you is I was trying to say this electron was in state 3 when I started shaking it. Now the electron goes to state number 2. Isn't that less energy? Where did the energy go? That's what gave off the light. Exactly. That is our photon giving off the light, right? And so this right here must be this change in energy. That is the energy in state 3 minus the energy in state 1 goes where? To the photon. How do I calculate the energy of a photon? HF. Do you guys remember looking at the atoms in the lab? That's why I gave you the cool glasses. Put them on again. If I were to put a simple atom up here, like hydrogen, and turn off the lights, what would you see? Would you see every frequency? You don't see every frequency, do you?
We only see the 3, maybe 4.
Yeah, if you see 4, great. Because that's all that's in the visible one, okay? But what I'm trying to get across to you is what you are actually then seeing. And here's the explanation. If you go back an hour and a half ago, I had 4 experiments on the board that we were hopefully going to explain before the day is over. The last one was the sharp spectral lines. The whole reason you see only a certain set of frequencies. Now, shut this off and turn this back on and we can look at some other atoms. Is because what is happening is I am putting the electricity into these atoms. These electrons are getting excited up to these higher states, is what we like to say. You might have learned it in chemistry as higher orbitals. And as they go into the higher orbitals, when they come back down, they must go from a higher state, which has more energy, into a lower state, which has less energy. That change in energy is the frequency that you saw. And I think you saw a red one up there, right? And there should be 4 in there, like a violet and a turquoise.
Why is it E1?
Oh, I'm sorry. My bad. I didn't mean E1. Yet. I meant E2. Because here's where it gets more complicated. Couldn't this electron have done that? And then it would have been E3 minus E1 equals HF.
No, wait. 2HF, right? Different frequency of light.
Different frequency. So this would be frequency, let me call it frequency from 3 to 2. And this would be the frequency 3 to 1.
When would it be 2x?
How do you know what H?
No, it would not be twice the frequency, would it?
No.
Isn't that energy different than that energy? In fact, isn't this from here to here 3 times the change of here to here? So here to here would be, I'll call it a factor of 4. Here would be a factor of 3. So this should be 4/3 of that one. And that's what I would get if I put in my n value of n squared. So it's not a linear relationship, right? It's a squared relationship. So I don't get twice the frequency. I get 4/3 the frequency. And you guys have a bunch of questions, but I'm not even done here. What else could happen?
Did it go from down to
You see, after this electron went from 3 down to 2 and gave off this photon, Then it will go from 2 down to 1, and it will give off another photon. And so from E2 to E1 would be another frequency. And so in this case, you would have 3 different colors that you would see. And I'm not even close to being done, because what else could have happened? It could have been at n equal to 4. And if it was n equal to 4, then there would be E4 to E3, or E4 to E2, or E4 to E1, or 4 to 3. I guess I already did the rest of them. And so this would be a frequency that would be 4 to 3. This would be a frequency that would be 4 to 2. This would be a frequency that is 4 to 1. Do you see all the different colors that could come from here?
Just 3 harmonics.
There is a lot of them, aren't there? Oh, you guys had a bunch of questions, so fire away. What?
And the delta E from like 3 to 1 is going to be equal to 3 to 2, but 2 to 1, right?
No, okay, let's do the general formula then. Your question is great, and the answer is no. But in general, it would look like this. If I had E at a certain state, say state N, and it transitions down to state M, then the frequency of the light would be calculated this way, from N to M. And what I would have, according to this equation, and I'll write it in this form, I would have N squared H squared over 8ML squared, transitioning down to M squared H squared over 8ML squared equals to HF from N to M. Factoring out like terms, I would have an N squared minus an M squared, HM. And I think that's what you're asking. That would be the general formula for any transition. Put in 5 to 4, 2 to 1, 3 to 1. And these would be all the different frequencies that are possible. Now notice that's a lot of them, but you only saw the ones that were in the visible range. And so let me emphasize, when you did this atom, you only saw a fraction of the frequencies that were coming. Some of these were in the infrared, some of them were in the ultraviolet, but the ones you saw were just 4, because those were the 4 that were in the visible spectrum. But there's a lot of them. But it's not all the frequencies. It's just whatever integer you want to calculate from here down to here. And I should emphasize, remember, this was a model of a terrible atom. If we have enough time, our atom will get better. And we will do a better calculation for a better atom. And I'm not really not even interested in doing a better atom. I'm just interested in, you got the concept now of where light comes from. Why quantum mechanics is called quantum mechanics. Because you're treating the electron as a wave. And like the sound waves, they were quantized. Our electronics, our electrons are quantized. Yeah.
Why do we see a full spectrum at the top and the bottom of the bowl?
You are probably seeing more complicated atoms interacting than just the hydrogen. In other words, you're seeing the hydrogen interacting with the tungsten that's inside. Let's see if I can answer that this way. I purposely put the simplest atom I could think of, hydrogen. Let's go helium. What do you think would happen if I put something like helium in here?
It has 2 energies. No, it only has 1 energy. Well, no, it has 2.
See how it gets more complicated now that we got 2 electrons jumping around here? Now again, what I've done for you has been a poor model of an atom, and hopefully before the day's over we'll have a little better picture of an atom. But what I do want you to see here is look at this one now. If you look at this one, we'll probably see a lot more colors. But notice they're also quantized still, right? And that's what I can't overemphasize here. We have this electron that we are now treating as a wave, and it makes a certain pattern in the atom. And how do you calculate that pattern can get pretty complicated. That's why you got to finish your Math 220 before we can show you more on how to calculate these things and how to solve wave equations. And I think you're learning that in your Math 220. But when you learn how to solve these, you're ready for the next step in quantum mechanics. But this is the first step of the understanding of why is it quantized. It is quantized because then these electrons are there. Now in this case there's 2 electrons, and so there's a lot more interactions that are possible. And a lot of these interactions are in the ultraviolet and the infrared. But you see, what, like 8 of them? 7, 8? 9? 10, a bunch? Yeah. And so that's the ones you see. Watch if I make it even more complicated. I'll turn on these lights here so I can kind of see here. Yeah, sodium, again, was real nice to us in the sense that it only has one, and you mean it only has one in the visible. And so all the other transitions just happen to be at energies that are higher or lower than the visible range that the human eye can see. And so we are lucky. There's actually 2, by the way, in sodium. They just happen to be at the same place. And so there's one here and then the other one here, and they happen to be the same, or nearly the same energy level. But the other one you looked at, and maybe I better stop here with the light bulbs, but I wanted you to see them, is that what if I make even something with more electrons? This is neon. And if you remember, neon's number 10 up there. So it's got 10 electrons with a lot of different transitions that are possible. And so it gets a lot more complicated. And so again, let's look at the colors or look at the light. Oops, that is not neon. Is that that? Well, look at it. I'll turn it off. Is that that might be krypton? Oh, excuse me. It's argon. Yeah, argon. All right. So there's argon. That's not the one I meant to grab. All right. Let's try this one. This one says neon. This is the one you guys saw also in lab. I don't think you did the argon in lab. Although, you notice the blue color. Do you remember, those of you who did 122, using the argon, the electron that we made go in a circle? And it gave off that blue light. That's why it was blue, and there wasn't a whole lot of colors. It was just in the blue. And so that's why we filled our Okay. Ignore that one too. I have to get these things better labeled here. Ah, there we go. Okay, there's what I was after. All right. So there's neon. And of course, you see lots of colors. But again, I can't overemphasize this. Notice that you see discrete sets of colors. You do not see all the colors. And the reason for that is explained right here with our quantum mechanics. And so this whole idea of the quantum mechanics, these 30 years that shocked physics, 1900 to 1930, this whole idea of thinking of these electrons as waves, just like we started to think of light as particles, now we're thinking of our electrons as waves. And once we start thinking of them as waves, then their patterns become quantized. Their momentum becomes quantized. In fact, there's something else really weird here that is worth mentioning. Look at energy state number 1. And maybe get away from the thinking of this as being an electron. Maybe we should think, as you guys asked earlier, I should think of this as being just the whole atom. Wouldn't the whole atom also behave as a wave because it is made out of protons and neutrons and electrons?
Wouldn't mean that everything, it doesn't mean everything that exists to be a wave as well.
Yes, but look at this lowest level. Can the energy level get any lower than this? So we call this the ground state. We call this the lowest state an atom can have. Okay, fair enough. But something new here that we haven't seen until quantum mechanics. Is it stationary?
Yeah.
Put in n equal to 1. What does this say about the lowest energy level? The lowest energy level, the lowest it can get is actually moving. Now let's go back a few weeks. What did we say absolute zero was?
Nothing moving.
We defined absolute zero as a point where everything comes to a stop. And that was perfect before 1930. But what we're seeing here is there is no such thing as stop. Things can't stop. The lowest speed they can have, when you're thinking of them as a wave, would be n equal to 1.
Otherwise it doesn't have a wave anymore.
Right. I mean, if I were to have no wave, this would be my model. Okay, here's no wave.
That's a spring.
But see, since the electron is the wave, if you have no wave, you have no electron. So to have something not moving only happens if you have nothing. But as soon as you have an electron, you have to have a wave. As soon as you have a wave, you have a wavelength. As soon as you have a wavelength, you have a velocity. This is the lowest energy. And so we can never have anything stop. And that is definitely new. So, guess what our new definition of absolute zero is going to be from here forward? Yep. The temperature of where everything gets into the ground state. The lowest speed it can have. Not stop. Forget that. We know it's not going to stop. Just like we know our heat engines from our thermodynamics are never going to be 100% efficiency. We're not even going to shoot for that. We're going to shoot for an efficiency based on the second law of thermodynamics, right? That's what we learned in thermodynamics. And what we're learning now is we're not calling absolute zero anymore where things stop, because they don't stop. We call absolute zero where they go the slowest. Now, granted, that'll be really slow. I'll run out of time, so I won't put in numbers, but you put numbers in here, and it won't be very fast. And so, up until this point, we never even made a difference between stopping and its slowest speed. It would have made no sense to me 6 weeks ago to tell you, absolute zero is not where they stop. Absolute zero is where they go the slowest. Because I'm sure you would have asked, well, can't they go slower than their slowest? But now I can answer you, no, they can't. This is as slow as they can go. They're waves. Yeah.
So everything that we can imagine and look at and experimentally touch, I guess, is all really just a superposition of some quantum mechanically smaller thing.
Oh, yeah.
Atoms and electrons are really just superpositions of whatever they're built up of, like their quarks and gluons and whatever.
Yes, yes. Now, just to show you a couple other pictures maybe here to kind of wrap it up, let me start with this one. This is a much better picture, and unfortunately out of time to do a complete justification for. But you remember I did the wave in a box? That really wasn't a good picture of an atom. Let's change that for a minute. Yeah.
In terms of looking at these energy states, you're using 10 to the negative 10, which is the width of the atom, right?
Right.
Is that the standard? Is that what you would like us to be sort of using for
Oh, okay. So if you're thinking about the test,
a little bit, a lot?
here would be a good test question. An electron is in a box of width 10 to the minus 9. I'll change it on you.
Okay.
I
So I see. You would give us that sort
Yeah.
of, you would give us that box.
So I'd give you the size of the box.
Okay.
And then I would say the electron is in state 4.
Okay.
List all the different frequencies
And we have all these different
that could come from this artificial atom. Fair enough? And so you would have to go 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1, 2 to 1. And then you go, oh, there's 6 different frequencies. And that's what I'd see when I put on my cool glasses. Right.
Can you use a factorial somehow to come up with that number?
I don't see it because it's squared in there.
Well, it seems like statistics, you have a certain set of combinations of all the different.
Do you mean the number of
sample size, right?
Oh, do you mean the number that would come from it?
I'm saying the number.
The number would be a factorial, sure.
It's based on the number of.
Yeah, the number of frequencies, but not the value of the frequency.
Yeah.
Yes, yes, okay, yes.
So what is the formula for that? That's what you just asked us, isn't it? How many are there?
No, I said, what are the frequencies? And so you would first of all realize there's 6 of them. That's the easy part. Then you would do each of the energy transitions 6 times and get the frequencies. Yeah.
How do you know what H is exactly each way?
How do I know what H is?
Yeah, it's different for each. Isn't it different for
No, it's called Planck's constant because it is a constant. So it's the same value for nature. We don't really know why nature has that value. Again, maybe that's one beautiful thing for you to discover. Because, you know, as science goes along, we always come up with a number, and then it's later on in history that we understand where that number came from. Usually because of some other number that we don't understand. And then so we make the next step and we the next step. But we don't really know why nature has Planck's constant in there. In some sense, it's probably good that it was small, because we would have, but then in one sense it's bad, it's so small, most of you have never noticed quantum mechanics before, and we don't live in that world, and so we think this is kind of a weird place. Well, I wanted to put this diagram on the board because this would be a spacing of the hydrogen atom. And I don't think we'll get time to actually then go through the calculation here, but I'll put it on the board nonetheless, that the energy comes out to be negative 13.3 electron volts over n squared. So if I improved my model and put a nucleus in it, I would of course get a different formula. So please don't confuse this formula here, which is my first attempt at explaining it, with this formula. Okay? This would be the energy levels here. Let me say a little bit about this formula, where it came from. It's probably best explained with this picture. Your author says, look closely at this picture. If you think of the atom not as being in a sidewall in one dimension, like we just did, but if you think of the electron as going in a circle, that black line, then what should happen is it should be a wave that is around the circle, and so what I must have is around the circle, 2 pi r must be an integer number of wavelengths. And that's what this picture is trying to say. Now again, I in no way am going to try to derive this for you in the short time, nor am I going to expect you to be deriving it on the test. But conceptually, I want you to have the same picture. This is my improved model of the atom. Instead of just taking a sidewall and a sidewall with no nucleus, let me make another step, which again is not the best way to get to an atom, but it's the next best step, is to do what we call a Bohr model. And say, look, here is the nucleus, and what will happen is the electron will go around it, and you have to have an integer number of wavelengths. What I want you to see is, do you see how it has to be quantized again? In fact, the picture next to it is the author's attempt to say, what if it was not an integer number of wavelengths? So just like this one, I had an integer number of wavelengths when I did this, or in this case, an integer number of half wavelengths. This one, he's saying as it goes around the loop, if you don't have an integer number of wavelengths, look what happens. If the wave starts here and goes around 1, 2, what the heck does he have here? 1, 2. Oh, it's supposed to go behind. Anyways, what he's trying to say is if you go all the way around and you don't get back to the same place, then on the second loop you would have destructive interference, and the third loop you'd have more destructive and more, you wouldn't have an atom anymore. So you can only have an atom when you have a set integer number of wavelengths. My example for you is this crazy thing up here. Partly is to get you to have a better picture of it, but partly is to show you that it's not anything magical about the electron. That's what I want to emphasize. The quantization occurs with every wave. The quantization occurs because we are treating them as waves. And so this little oscillator, if I power it up, and let it shake, this right here is now shaking at a frequency of 64 hertz on this dial. And what will happen is it will make waves, and unfortunately this one's not quite the same as this one. This one's making waves go in both directions. But if they do not add up constructively, they will keep going around and add up destructively. And I bet from your vantage point, when you look at this ring, it doesn't even look like it's shaking much, because we have destructive interference. And I would say I have no electron at that frequency. If I change the frequency to just the right amount, and I don't know if you guys at that angle can see it, and at that angle can see it, but now I actually get a standing wave pattern, and I actually get an electron. And so the electron actually exists in this pattern. If I go to a different frequency, maybe I'll go down. Oh, here's a good one. Yeah, it'll really vibrate in that one. And so there, I do not have destructive interference. I have constructive. So I would say this is one pattern that is possible. And if I went through the math, I would find the equation for the energy based on the wavelength, based upon the circumference of the circle. And so different frequencies are possible. But not every frequency is possible. So there's the higher one. See if we can even see one more higher before I show you one more last thing. Oh yeah, there it is. And can you guys see it? Okay, and so there is a pattern. And so that would be the next possible set of waves that are possible. And again, that's really what, more than anything else, conceptually I want to get across. There is a quantum effect because of the wave nature of the electron.
Is it a coincidence that the standing waves are 1, 3, 5, and now 7 on this?
On this one, they come out to be the odd ones because I've pinched them here and not here. So this is a node, and they're going both ways, so I have to get odd numbers only. Whereas in this model, I wouldn't really have that. So my model only goes so far. Well, then in the last few minutes, let me show you one more set of patterns. It's this one here. It's really the same apparatus. It's just, I like it because I think you can see the wave pattern a little bit better. I'll start with just listening to it. If I were to Can you hear it get really loud right there? But if I get off of that frequency, it's not really loud. Why did it get really loud right there? Because the wave pattern that is formed, the center that is going up, is then sending the waves out to the rim and reflecting them back down. So this is a two-dimensional picture of an atom. So this is kind of a one-dimensional picture. This is a two-dimensional picture. Obviously, a real atom is still more complicated than all of this. So we haven't quite gotten that far. But here's what's neat about it. If I switch this over to video and turn it off and turn it back on. Well, that didn't help. I'm plugged in, aren't I? This has done this before on me. It shuts off. No, go on, go on. No. Well, it's not that. I can't even get it to go on. Power on. No, all right, good. Okay. Yes, okay. All right. Thing always confuses me. It's got two power switches. Okay, now, what if I put a little bit of sand on here? You will hopefully see that the sand just kind of settles across the page, right? And the reason for that is I really don't have any ripples. I don't have any waves. What I'm trying to propose here is that this frequency, I'm close. This frequency of 924 is far from the pattern that will form. Go back to the pattern that formed, where it got loud. Yeah, and you will see the pattern. You will see where the nodes are, where the pieces of sand fall into place, because every place else, that little metal plate is bouncing up and down. So I would call this probably 1, 2, 3, n equal to number 3. This is the pattern that I have. Let's try another pattern. This would be like the electron in the third orbital. If I go to a lower frequency, they would fall into place based on their pattern. So again, there's a certain set of frequencies that are well defined. And it's those frequencies that lead to the wavelength, which lead to the velocity, which lead to the quantized nature of it. And so this is orbital number 2. And so I have just changed from orbital 1 to orbital 2. And if this was an electron in an atom, then if I knew those energies, I could calculate their difference, set it equal to the photon that is given off, and I can put together my photons with my electrons, right? Let me go to a lower frequency. Lower frequency. How are we doing on time? Huh. And so there is the lower frequency, and I've kind of put some more on there since a lot of it has come off. And so in the moment we have left, we'll just go the other direction. So that was n equal 1, n equal 2, n equal 3, you saw that one. Let's go higher. N equal 4. Should I go higher? Okay. I got to go to a different scale.
Push it all the way.
Right about there. What's that? Is that a 1, 2, 3, 4, 5? And so there's 5. Oh, that's loud. Should we try 6? Is that 6? 1, 2, 3, 4, 5, and the 6th one is actually real tight now. It got so tight you don't even see it. But whoa, I'll shut that off. Yeah. Anyways, hopefully that made somewhat of a sense to you, and that's our that's our quantum mechanics. All right, come up and ask me a question. All right.